Podcast is now starting. All attendees are in listen-only mode.
Hi everyone, this is Zaid Rawi from BP. Welcome to this Icheme Process Management and Control Special Interest Group webinar. This one is sponsored by IPCOS and is on optimization of process control strategies for steam networks using dynamic simulation. Our presenter is Juan Carlos Duarte Triana from IPCOS. He's a practitioner of advanced process control for over 10 years and graduated from the National University of Colombia with an M.Sc in chemical engineering, and has worked as a consultant in advanced process control in both Colombia and the UK. And he's been working in IPCOS in the UK since 2013. This presentation on steam networks control will cover the details of a steam network whose process control philosophies were optimized using a rigorous dynamic model. And the objective of the study, and doing that, was to understand the impact of changes in the topology of the steam network, and also analyze the dynamic impact on the steam network of choosing different control philosophies. The study resulted in several benefits, such as improved understanding of the steam network and dynamic interactions, and how better to operate the system to improve steam network pressure control. Please, as the presentation goes on, type your questions into the question and answer pane, and we will leave time at the end to answer those. And I will now hand over to Juan Carlos.
Okay. Thank you, Said. Thank you very much for the introduction. Yes, well, as Said mentioned, then I've been working with advanced process control for the last 10 years. But on top of that, I have also been involved heavily on some of these projects in which we do study the control systems of different processing companies, and to do that, we don't only just go to the specifics of the control system, but we sometimes need to then do a very, very deep understanding of the process first, to then be able to try and optimize the control systems. And such was the case in this situation, in which we were asked to try and help them figure out what the impact of changing some particular equipment in the steam network would have in the network behavior itself. So, okay, let me continue. Well, sorry, this is me. Just for you to have a reference, that's my name, and the company I work for, IPCOS, has been in the market for many years. Now, let's jump into the details. So I will do first a description of the process, so we all know exactly what is it that we're talking about. And then after that, I will do a description of some details on how did I build the simulation. So, basically explain the assumptions we did and maybe the reasons why we did those assumptions. Then finally, we'll look into the real-time data match and then some results that we already obtained from the simulation. It has to be said that this was the first part of the project. I mean, now we have the results. Then this year, during summer, they will do the specific changes in the network, and they will have to implement the recommendations that we provided with this project. So that we'll also be providing some support. So for those who know any Dutch, you will quickly know that what I'm showing here is partly in Dutch, and this is because the place where we did this is a chemical site. It's actually a chemical complex in the southern tip of Netherlands called Geleen. That's a city. In this complex, there are many industries, chemical industries working. But what they have done is they have appointed a company to manage all the utilities of the complex. So all the sites use the steam, for example, that comes from the common grid. There is a common grid of steam that has been built for all the companies in that site. So different companies buy steam from this supplier, which of course has its facilities in the same place. And that you will see in the topology of the system. So they actually have divided the whole network into two regions, like it's called the northern part and the southern part of the network. And then, as you can see in the northern part of the network, they have two boilers, both with a maximum capacity of 150 tons an hour of steam. And then they have another boiler working at the moment, which is basically in the middle of the network, providing up to 300 tons an hour of steam. As you can see, that's the existing boiler. And the big change they want to do is they want to remove this middle burner. I mean, this burner that is in the middle section of the network, and actually install a new boiler in the southern part of the network. So you can see the distances. Basically, from the north to this middle section, there's pipe for up to 1.5 kilometers. And then from that middle section to there's a T-junction here where the steam gets divided into one of the main consumers, which is an ethylene plant. And this ethylene plant is 1.5 kilometers away. But from that ethylene plant to where the consumers in the south are, you still have another 1.3 kilometers in total. So basically, if you add up, this is 4.3 kilometers that you have from the north consumers, so from the north boilers to the south consumers. A lot of things can happen to the steam in 4.3 kilometers. And that's what they want to know. On top of that, and I will get into detail of that, but the way the steam flows is not the same if you have a provider in the mid part of the network than if you have just in the south part of the network. So the big change again is to remove the provided from the middle part of the network and replace it for a provider in the southern part of the network. So that will change all the dynamics inside. It's a long pipe, so there are many things to consider in that situation. Okay, now let's continue. So let's then first talk about what were the main assumptions we did for the simulation. Well, first of all, although it's not mentioned here, I will mention it. The software we used to make the simulation was Aspen Heis's Dynamics in its latest version. At least at the moment, we use version 9.1, if I recall correctly. So we use Aspen Heis's Dynamics to develop all the bits and pieces of this simulation. And what covered the simulation is basically the same extent as what I just described. So in the simulation, we did the two north boilers, the network, the middle boiler, the southern boiler, and the main consumer. All of them were simulated, as well as the consumers in both north and south, which are basically, you will see, just simulated as outflows of steam. So what did we do for each one of the boilers? And that basically extrapolates for all four boilers, two in the north, one in the middle, and one in the south. So the boilers were simulated assuming that both the radiant and convective sections can be approximated to heat exchangers. the thing is, with high-sys dynamics, you have limitations in how much can you use the fire heaters block that already exists in high-sys dynamics. But yeah, you don't get to play too much with it. It's actually more intended to be used to size new fire heaters, not too much to do dynamic simulations with it. So that's why we had to take this approach. And in any case, one of the biggest interests in this particular situation was how the network would respond in terms of pressure profiles across the steam network and temperature profiles across the network, much more than the specifics of the internals of the boilers. It is, of course, important to simulate the boilers as accurately as possible, but we believe that the assumption we did with this approximation of just making both the radiant and the convective sections heat exchangers is enough, because if you see, we are also using a steam drum. I mean, we have a separator here, which is basically the same as the steam drum in the boiler, and this one, for example, has exactly the same size as the steam drums of the particular boilers. And usually most of the dynamic impacts that you can get from different boilers are related to the volume of the steam drum. So this matches perfectly the steam drum volume. And we also made sure that the control structure that we are using is the same control structure they have. So for example, in their particular case, they have a 3-element control for the level of the steam drum, and that we did. So you can probably see here that for this particular steam drum, we are in fact having a 3-element control. So the level control goes to a flow control that controls the boiler feed water flow. You cannot see it here because in high-sys, the feed forwards to PID blocks are not shown in the schematics, but in the internals of the block you can see. And in this particular case, we were using this outflow of steam as the feed forward action for this level control. So the 3-element control structure was there. That means that if both the controller, the original controller is exactly as it is in the plant, and the steam drum level is as it is in the plant, well, chances are that the dynamics of the boilers are well represented. As well, we did the superheating section here with another exchanger. As we said, the convective section was another heat exchanger, and there's this superheating also has a specific control, which you see is a temperature control that we just did as it typically is. It's just injections of boiler feed water to the superheated steam to keep a specific temperature of superheating. Then, yes, so that covers, let me go back, that covers how did we do the simulation for these 4 boilers. And then the other important part of equipment that we have here is this huge turbine that they have in the olefins plant that they provide steam with. So that's another bit that is very important to simulate, because this part in particular consumes roughly 50 to 60% of all the steam produced. So that's why it's so important. It has a huge impact on the behavior of the steam network. So that turbine was simulated as accurately as possible. So the turbine was simulated using actual performance curves of the machine. Yeah, and as is the case there, they do have, that turbine has attached to it a governor that keeps the power of the machine constant. So that's exactly what we did in this case. We did a special PAD loop that basically was acting on the steam to keep the power coming out of the machine constant. Why did we want to do that? Because to simulate this particular section, and that we discussed with the client, to simulate this particular section is really important to be aware of the quality of the steam. So it's not the same to have 70 tons an hour of steam at, I don't know, 470 degrees. By the way, this whole network is a network that is intended to work at around 120 bar. That's very, very high pressure. This is a 120 bar steam network. So not only is the flow of steam what's important, but the quality. So it's not the same having 70 tons an hour of steam at 470 degrees than having that at 490 degrees, because the amount of power you can extract from the steam varies and varies significantly. So we wanted to be able to represent that. So what happens if the quality of steam degrades or upgrades? So that will in itself make the consumption, the net consumption as mass of steam change in this turbine. So the only way you can represent that is by actually using real performance curves for the turbines. And so that's what we did. And then finally, if you remember, we talked about more than 4 kilometers of pipe that we see in this network. And this is one of the biggest worries for them. I mean, the things that they really take a good look at, and is the fact that because it's 4 kilometers of pipe, although of course they're insulated, and I mean, they take all the precautions that they can try and have. In any case, 4 kilometers are enough for you to first lose a lot of head. I mean, there's a pressure drop across all those kilometers of pipe, but there's also loss of heat. So since both the head and the heat loss need to be properly estimated in order to find cold spots specifically, then we had to basically, use these special blocks in HYSYS, which allow you to dynamically simulate compressible fluids. So HYSYS has this specific block that allows you to simulate pipes with compressible fluids inside. So we can show all the dynamics inside the pipes. And not only that, we did our job as well to use data from the plant to try and estimate as good as possible both the friction across the pipe, so the pressure loss across the pipes were accurately represented, and also we took data from them also to try and estimate the heat loss. So for each one of those sections of pipe, we estimated heat transfer coefficients. So with those heat transfer coefficients, we were able to see how much heat was being lost in each one of the sections. And why is this important? As I mentioned, the most important thing for them is the cold spots. And the cold spots are generated when you have one of these sections with a low flow. So if the flow is low, then of course the amount of heat loss has a stronger impact on the temperature of the steam. And one thing that you need to avoid at all costs is some spots in which you can have condensation. You can think, okay, well, this is superheated steam. Will it actually condense? Well, they have noticed that in all these pipes, in general, if the flow of steam falls below 10 tons an hour because of the length of the pipe, it is possible to find cold spots cold enough as to you approach the condensing temperature. So that's why this was so important. So let's see, how did the data match? So these are 4 very key variables that we had to check if they were in agreement with the real. And as you can see, the pressure downstream. Why is the pressure downstream a measure of how accurate the simulation was? Is because the pressure control in this moment is done done in the north. Basically, I call downstream south because it's basically the end of the network at the moment. Before installing the new boiler in south, the south part is the end of the network. So the pressure in the south section, let's say, the real-time data shows us values of typically 121.8 bar. With the simulation, we were reaching values of 122.5. Yes, a little mismatch, but in general, it behaves the same way. Boiler outlet temperature is basically the same. The temperature downstream, this is also then a figure of how accurate is the heat loss. The first one is a figure of how accurate is the heat loss represented in the simulation, and this other one is how accurate is the figure of the heat loss. As you can see, it's also very accurate. And then the temperature in the middle of the network. So these bottom 2 tell you how good the simulation is being able to estimate the amount of heat loss. So let's go and see some initial results, for example. So one thing, as I mentioned, is to check whether or not you have cold spots. So HYSYS allows you in this compressible gas sections of pipe it allows you to estimate, or it actually calculates for you a temperature profile inside, temperature and pressure profile inside the pipe. So if you see, this was the result of the simulation when we were doing actually one specific task they need to do at some points, and it's they need to do flow reversal. With this, what I mean is at some point, sometimes because of changes in demand, a specific section of the pipe has to change the direction of flow. So if initially the flow was flowing from north to south, well, that section then needs to be changed to flow now from south to north. So when that happens, that's when you have the higher chances of cold spots. So HYSYS actually allows you to simulate how cold can the pipe get at some particular moment. So you look, if you only consider inner and outlet temperature, you can be fooled. You can see the inner temperature is around 480 degrees and the outlet temperature is around 470 degrees. So you can be fooled and think that things are fine inside the pipe, but with the simulation you can actually know that there will be sharp changes in temperature in the inner part of the pipe that can cause issues. So you can see that in this particular case, at around 200 meters inside the pipe, there will be a spot that has 420 degrees. Naturally, you cannot put thermocouples every 100 meters in the pipe. That's not practical. But if you have an accurate enough simulation, you can simulate those scenarios and get to know these details. So this was very important for them, because with this tool we were able to actually create some special protocol. So whenever they need to change the flow direction of steam in sections of the pipe from north to south to north, then we know now with a good degree of accuracy how fast do they need to do it. So they can instruct operators on how fast do they need to do this change to avoid the cold spots. And that's really, really important, because this will tell you when is the pipe actually getting close to the to a temperature that is a danger for possible condensation. Right. Some other interesting result that came from the simulation was well, the whole idea here was to try and evaluate how the actual control system was going to react to those changes. And one thing we found, for example, was that the pressure control, let me go back to the initial slide. The pressure control that we have for the network, this pressure control uses a feed-forward action. And this feed-forward action, the way they configure this feed-forward action is basically using the material balance. So this feed-forward action is nothing different than just adding up all the suppliers and adding up all the consumers and do a subtraction, just pure material balance. So basically what this feed-forward action is telling you, that calculation basically sends a signal to the pressure controller, and that is telling the pressure controller that the network is in balance or out of balance. So if the network is out of balance, then of course it immediately starts increasing the action of the network, like anticipating to the effects of the out of balance situation, because, well, in any steam network, the pressure of the network is nothing different than just a representation of the material balance of the network. So if the network is out of balance, then this will be pointed out by this feed-forward calculation, and then it will act accordingly. But we noticed that because they're using the full material balance, well, they were mistakenly using the action in the sense that since the feed-forward action is using both all the suppliers and all the consumers of steam, then part of the feedback control was actually inside the feed-forward action. Let me explain this. The pressure control, the effect of the pressure control is to change the amount of steam produced by each one of the boilers. If that steam produced by the boilers is part of the feed-forward calculation, basically you're looking at yourself to make the feed-forward calculation. It did work for them, but it worked only to an extent. They were not able to make this feed-forward action strong enough as to really see a big improvement in performance. And we simulated this. This K that you see here, KFF, is the feed-forward gain. So we checked and tried different feed-forward gains to see if we see some improvement in the performance of the control. What you see in blue is the PV of the pressure of the steam network. What you see in magenta is the set point. So every time there's a disturbance, you see the disturbance, and you see this one in the bottom is the output of the controller, of the pressure controller. So you can see that even though if you increase the feed-forward gain, you don't see a good improvement in the performance of the loop. And the reason for that is what I just said. It initially gives you a dynamic advantage, but the moment the controller starts reacting, the moment the pressure controller starts correcting, that information then is consumed back again by the feed-forward action. I know this is a bit confusing, and you can contact me later for details about this, but basically it's like a dog chasing its own tail. So it doesn't really work. So for as much as you try and increase the feed-forward action, this is not improving the overall performance. So what did we do? Well, we then thought about making a change, and this change was, what if instead of using the full material balance, we only use the consumers? We only use the disturbances on the network. Because in that case, you're not looking at yourself, you're only looking at the externals. So because there are measurements, flow measurements in each one of the consumers, So it's easy to see that when a consumer changes demand, then you can immediately react with your pressure controller by increasing the production of steam. So it's very simple, and we did see the effect. So you can see here that without the feed forward, this is the new feed forward strategy that we are proposing, and they accepted. Without the feed forward action, then when you have a change of 10 tons an hour of steam in demand in the south, for example, your pressure can decrease down almost 1.3. I think this is 1.3 bar. You see a reduction. There's a sudden reduction of 1.3 bar in the pressure. That's without the feed forward action. But if you have the feed forward action as we propose, then the same change in 10 tons an hour actually only causes you a small change of 0.4 bar in pressure. So this is a significant reduction in variation. It really helps you to anticipate the action. You can see here the action of the controller. First is just basically on feedback, trying to get the pressure back, and actually after that it needs to go back a little bit. Here is very, very accurate. Once the disturbance comes, immediately the pressure controller knows that it needs to react, and it reacts in anticipation, and you see that the pressure, of course, it reduces much less. So this reduces the disturbances. So this was one of the biggest advantages of doing the simulation, that we were able to see that the current feed-forward strategy that they had was not the right one, and that we were able to compare between that one they had and the one we were proposing. And this will for sure bring a lot of robustness to the network. Apart from that, we were also able to evaluate new control strategies, one of which is one that is typically implemented in every single set of steam boilers, and is the ability to bias the boilers. What does it mean? What do we mean by bias? It turns out that if you have a pressure controller, a single pressure controller that is commanding several boilers, if you have a specific issues with one of the boilers, it is important for you to be able to make some of the boilers work harder and some of the boilers to produce less steam. So in order to do that, it is good to have some special block in the DCS that allows you to bias the production. So it still receives a single signal of load in each one, but you can add or subtract to that signal. So that way you can, for example, choose one of those boilers in the north and say, okay, I want to produce a little bit more with this boiler. So the moment I start increasing this value, then the other boilers start reducing production to match the same amount of steam produced. And then we checked stuff like it was important to do a bias tracking when it's not in cascade. So for example, if one of the boilers is working with, let's call it in manual, is not attached to the pressure controller, it's still important for this value to then be calculated. So then it can seamlessly be back online if it's needed. So let's suppose this south boiler, they put it back in manual. If this is in manual, then the steam production will change because there are disturbances. But then to be able to always put back the boiler in service, then it's important for this bias value to change it automatically. So this is something we develop for them. So we developed some calculations and some logics for them as well. And then finally, again, the biggest worry for them was the cold spots. And as we discussed before, those cold spots are caused by low flows in sections of the pipe. So we developed a special control strategy, which is the one you see right now, that avoids automatically avoids these cold spots. And how does it do it? Well, what it does is basically it measures the flow of steam in this particular section of the pipe. It also measures the temperature at the exit, and then comes and acts on this. This is a low selector block in the DCS. So it competes with the pressure controller for the control of the specific boiler, if there is the case in which the flow of steam through this section of pipe is too low. So let's suppose the flow of steam in this section is starting to get too low. So if it's very low, then at some point what happens is this flow controller, which let's say at the moment is not the one selected, then this flow controller starts becoming in action, and once it comes into action, then what it will do is it will start commanding the boiler to avoid the flow from reducing any further. So then the operators don't need to even look at this. It will automatically do it by itself. So if there are changes in the consumption, and remember, steam networks are dynamic, are very dynamic plants. So these changes here happen in minutes, if not seconds. If, for example, there's a huge change in the consumption in the south, well, one thing that will happen is that then the flow here will start reducing. If the consumption in the south reduces, this flow starts reducing. But remember, the flow cannot go below a certain value, because if it goes below a certain value, then you have risk of condensation. So in that situation, since the consumption in south is reducing, then you will see the pressure controller sending lower and lower signals to the specific boilers, because if there's less consumption, there needs to be less production. But as this happens, then what will be the case is that maybe the flow here is too low. So then in that case, once it reaches that low limit, then this flow controller will take action, and then will actually guarantee that this boiler is in fact starts producing even less. So then the flow that comes from the north increases. It's a bit confusing, I know. Again, for details, you can contact me. But we simulated this situation and actually developed also some logic. So it was not only this schematic that we provided them with, we also provided specific details on how to implement this type of systems in the DCS. And then you can see here that, yeah, in green we have the flow through the pipe. So we have a big change in the consumption. You see how it suddenly drops, but the moment it drops, immediately then we have the flow controller, this flow controller we were mentioning here, that guarantees a minimum flow, and that flow controller then takes over and then recovers the flow. And it's important to see that the set point here was around 30 tons an hour. It allowed it to go to around 27 tons an hour and then recover. Yeah, I mean, it is as fast as possible. And then what it does is it just controls the flow in a way that it doesn't go below. So then takes over the production of steam in that particular boiler. So this was really important, and they were really pleased with this, because now they can have this system that will make the whole network a lot more robust. So conclusions. Well, even for very fast process dynamics with lots of disturbances, which is the specific cases of a steam network, a dynamic simulation can be configured and used to troubleshoot process control problems, as I just discussed. The impact of big changes in processing units can be anticipated, and solutions to new problems found with simulations. And I think that's what I started with. Look at what we saw. This is a huge network. We're talking about over 40 kilometers of pipe, and they're actually removing a huge steam boiler and replacing it with another. And if let me go back quickly to that. The point at which this steam boiler was compared to the location of this new boiler, we have 2.8 kilometers of distance between them. So the impact in the network is important, and that we were able to simulate as well. So because of this, we can then guarantee that the downtime of the units can be reduced when you have robust controls in place. If you don't have a robust control like this one, that helps you guarantee that the flow through your pipe is always at least a minimum amount that guarantees no condensation, for sure that increases the robustness of your overall system. And well, we will provide support during the implementation phases, because not only we have the expertise to develop this type of simulations, but also we have the expertise with the control systems, so we can help implement this. And we estimate the reduction of variability up to 80%. So again, it all goes in the direction of increasing robustness of the controls and a much better understanding of the process. Okay, that's it. Thank you very much.
Thanks, Juan Carlos. You might want to pop your contact details up at some point, just so people can see that, in case they want to ask any follow-up questions.
Okay.
So we'll go to the questions and answers now as well. So please feel free to type your questions into the question and answer pane, and we will endeavour to answer those. While we wait for those questions to appear, I'll just ask a few, Juan Carlos.
Okay.
Could you elaborate on how long this sort of project took, including the modelling phase and then the upgrades to the control systems?
Yeah, sure. Well, the project was divided into 3 phases. The first phase was basically just collecting some data. Then there was a second phase in which we did a first model in HYSYS, and we ran a lot of cases, basically case scenarios. And then once we run all these case scenarios, we then came with solutions for the possible problems that we saw in the case scenarios. Then we went to the third phase, in which we implemented all those solutions in the simulation, and run more case scenarios just to see how robust were those solutions. What we're talking about here is, in each phase, we spent around a week at site. So it was 3 weeks at site, basically gathering data and running case scenarios. And there was, of course, the component of developing the simulation itself, which in total took around 4 weeks. So from start to finish, a project like this can be done in roughly 2 to 3 months. Yeah, of course, there will be moments in time in which neither them or us can work on it, but yeah, this we started last year around June. Yeah, end of June, and then by October we were finished with this. So it goes quite fast, because yeah, you can progress very fast. And again, there were times in between in which we were not specifically working on it, especially because this is just to anticipate future changes, so we were not in a rush. But I would say, yes, from start to finish, 2 to 3 months is a good estimate.
Okay, thanks, Juan Carlos. I can see questions are starting to come in. Please keep typing away. I'll wait for a few more to appear. I'll just ask some more of my own. Could you just remind us what was the hardest parts to model?
Yes. Well, I think one of the most challenging bits to model was in particular the turbine, because yeah, we had to really get to. I mean, it was more about gathering the data, very accurate data of the performance curves of the turbine to be able to represent accurately the behavior of the turbines dynamically. Yeah, but as well,
Okay.
once you simulate, you see a lot of PID controls there. So all those PID controls need to be tuned. So it is also an interesting exercise to make the whole thing robust, because although it's a simulated scenario, I mean it's a simulated system, you can still do wrong. You can still do a wrong PID control and then make the whole thing dance up and down.
Okay, so I'm going to go to the question and answer pane now. So first question is from Yangzong Hong. So he's asking about steam hammers. Did this simulation look at that possibility of steam hammers occurring? Would a HYSYS dynamic model be able to show that this phenomenon exists in operation of a steam network like this one?
Yeah. Well, not in this particular case. We didn't see the steam hammers. Sorry. But for sure, the dynamic simulation. I mean, what we did was we did strong tests. I mean, in which we were changing very quickly demand or production of steam, and we did see what the dynamic impact of that was in the pipes. So, well, it needs to be said that this is simulating a gas through a pipe. So yes, it will show you the pressure profile inside the pipe. So that's those. I would say it would be possible to see the effect of those steam hammers, as he says. I don't know if that answers the question.
Okay, well, thank you, Juan Carlos. Well, maybe he'll type follow-up one. Okay, so a question from Daryl Simon. He's asking about one of the graphs. I'm guessing it's the graph temperature versus axial length.
Okay.
On my deck, that was 8, I think, but you might have tweaked the order. It's 9 for you. Okay. So he's saying the graph reflecting the decrease in temperature at low flow rates. Maybe it's not that graph. Is the graph correct in the temperature decrease then increases? What was the explanation for the subsequent increase?
You mean this one?
I'm not sure which graph it is. Sorry.
Yeah, I think it's this one.
That's actually a length, not a flow thing. Daryl, if you want to direct us to the right one with another follow-up question, please do so. Anyway, you can explain this one in the meantime.
Yes. Why is it decreasing and then increasing? It's because this is when we were simulating a change in flow direction. So initially the steam was flowing from north to south, and this is when they started to change the flow to then go from south to north. So what happens is, because you're changing the direction, there will be points inside the pipe in which the flow dynamically, at least at moments in time, the flow will be almost zero. So that's why you have those cold spots. So that's why it goes down and then goes up. Basically, it's like you're having a flow of, let's say, 10 tons an hour from north to south, and then suddenly you change it, and now you want 10 tons from south to north. Things don't happen immediately. So there is like a competition for a hydraulic competition inside the pipe, and then what you will see is that gradually the flow will start going from south to north, but still a first section will still be going from north to south. So that's why you see that at some point it falls and then goes back up again. Basically, what you have here is then the hot steam from south. That's the one that is causing the temperature to be high at the end, You have the hot steam from the north, with then that making the temperature being hot at the entrance. But then because the flow inside the pipe basically collapses, then you see points in the pipe in which the temperature decreases because the flow is very low at that point.
I guess on this graph you could have had some other dimensions shown as well, maybe make it. But I think that makes sense. Daryl confirmed this was the graph that he wanted to look at.
Yes, I mean that will be. This would be nice to see in a dynamic way, in the sense like you can do the experiment and see how this graph, it just goes with time, and we saw that. We saw in the simulation that once we did the change, this graph was changing as the simulation was running. This graphic was slowly changing until the whole profile changed. So basically, the thing is, when you have flow through a pipe, of course, then the hot part is the one that is receiving the steam, and the cold part is the one that is, exhausting the steam, let's say. But because here we're changing direction, that's why you see this.
Okay, thanks, Juan Carlos. Albert Alvero has a question on backflows and what backflows were considered in the study. He has some follow-up points. Are there backflows from consumers going to the boilers, and has the site considered adding piping components such as check valves to prevent this from happening?
Okay. So let me think again. Yeah, what backflows were considered in the study? So with backflows, what we mean is just sections of pipe. Let me go back to this part. Basically, what we're saying is sections of pipe such as this, this section of 1.3 kilometers, that if you have your consumers in the south consuming enough, typically you will have flow from the north to the south. So backflow is when it starts going from south to north. I think that's clear. Then let me just a second. I just lost the question, but anyway, so these are the backflows we're considering. Basically, the change in direction of the steam flow. And what was the rest of the question? Sorry.
He also wondered if there were any consideration of check valves to stop backflow.
Yeah, no. Of course, in this case, a check valve was not considered because these pipes are actually supposed to be able to withstand these changes in flow. Because if you put a check valve, then you lose one boiler. It's dangerous, especially if, for example, we have the south boiler working in tandem with the two north boilers. It means that this south boiler is part of the pressure control of the overall network, the overall pressure control of the network. And if you put a check valve, then you will have a boiler that will change production, and you will not see the effect of the changes in production in the rest of the network. So it's a boiler that will be responding to changes in the pressure that may actually be caused by a north consumer. But if you put a check valve here, then because it's the boiler in the south and what is changing, is actually that steam will not go through and go back to the north section of the network. So that's why there are no check valves in that situation. If you would like to do that, you would actually need to implement a new pressure control for the south, just to control the south pressure. Basically, that would isolate the south pressure, the south from the north.
I think Albert's asked a small follow-up question where he's basically wondering if there's any equipment that's at risk from backflows and if there are any mitigations for that, and was that considered in the simulation?
Yes. The pipes themselves are on risk. That's why the cold spots were something we were really focusing on, and The mitigation is exactly what we described. Basically, changing the flow direction needs to be a conscious decision, a conscious choice. Otherwise, that's why you have this control system. That's what we call the anti-backflow system. Just part of the control system that isolates that the boiler that is closer to the section where the backflow may occur, and guarantees that the flow keeps on flowing on the same direction. If they decide to make the change of direction of the flow, then in that case, they need to manually do the change themselves. It needs to be a conscious choice. I mean, this, as it is designed, this just keeps the whole thing robustly working, probably not in the best way, but it is robust. If they really decide then to change direction, they need to then manually do the changes themselves. And not only that, that's why this is important. They have to develop a protocol, and they actually already developed a protocol to do the change in flow direction. So those are basically the two things they do to mitigate the impact of this. One, having a system in place, a control system in place that guarantees that no backflow is going on. And if they actually want the backflow, then they need to consciously do that and basically execute a protocol to change the flow direction, which means they need to change the production by a certain amount of time, so they can guarantee that you always have good temperatures inside the pipe. Okay.
Thanks, Juan Carlos. So Mark Evans has a question regarding quality of the modeling. So you had a slide early on that showed the match between the model and the actual plant.
Yes.
He wants elaboration on that. Do you use a method and metrics to determine if your modeling is good enough, or do you just do the best you can with the data available?
No, for sure. We did use data from the plant, basically. Well, what I was showing was just highlights, but we took dynamic data of the plant and compared that. Basically, what we did is we took real case scenarios of the plant, real operating conditions of the plant. The plant provided us with data they took from the data historian, and we used those trends basically and tried to replicate those operating conditions in the simulations, and then we saw how well did they match. Of course, we did a statistical comparison of them, basically in terms of standard deviation and things like that.
Okay, great. And then just a couple of minutes left now. So another question from Harsha Joyce. Are there any letdown stations in the system? And if so, were they considered in the simulation?
Yes, all this, what we call consumers, some of them are actually letdown stations. So, sorry. We have these consumers in north and consumers in south. I'm just summarizing because there were many of them. All of them were simulated. But some of them were actually letdown stations, yes.
Okay, great. So we've reached the end of the presentation. So thank you so much, Juan Carlos, for doing that. Everybody, when you exit, you should get a survey to review the webinar. Please do that and give us ideas as well for the future. So it was really good. I'd also like to remind everyone that we have the Advances in Process Automation and Control conference coming up later in the year, a physical conference, 18th to 20th of November in Manchester. So it would be great to see you there, hopefully. And I'd just like to say one final time, thank you very much, Juan Carlos.
Thank you very much.
Okay, goodbye, everyone.
Goodbye.